this video, we talk about so-called weak instruments. We have previously gone through all the necessary steps of IV estimation. That is, what is the first stage, what is the reduced form, and what are the necessary identification assumptions. And when you attend conferences or seminars and anyone presents an IV paper, then typically a lot of the discussion is about the identification assumptions, namely the conditional independence of the instrument and the exclusion restriction. And the reason why we discuss this so much is because these assumptions are not testable, or we can only bring evidence to corroborate them, but we cannot prove that they're true. However, there is also another issue with a potential problem with IV estimation, and that is the strength of the first stage. Now, the strength of the first stage is something that can be tested. After all, we can just run a regression of the regressor we're interested in, the endogenous regressor, onto the instrument and controlling for all other variables that we also control for in the second stage. But we need to understand under what conditions an instrument is actually strong enough to allow us to draw any meaningful inference about the effect that we're interested in. And it turns out that this is actually not so easy to do, or not as easy as one might think. Right? The traditional way of doing this was to run exactly the regression that I mentioned. So to run basically a first stage regression, look at the coefficient of the instrument, or if it's more instruments, look at the joint significance of those few coefficients. And if the F statistic of that test of joint significance was significant, then we would conclude that the instrument is strong enough. But I will show you here in this video that it's not that easy. And to know why it's not that easy, we need to first go deeper into what is the problem with weak instruments. Once again, an instrument is considered weak if it only has a very small effect on the actual regressor of interest. Okay? So because remember that an IV estimator only uses the variation in the regressor that is explained by the instrument. So if the instrument doesn't explain much of that regressor, then we cannot probably draw any meaningful inference. So there are actually three problems with weak instruments. The one is that for the reason that the IV estimator only uses a fraction of the variance of the overall variance in the regressor, you get it increases the variance of the estimator. So your standard errors will get bigger. And also, as I will show you, the standard errors are actually not so easy to calculate to begin with. That has nothing to do with the maths being difficult. No, it's because we don't quite know what the right standard errors are. The other thing is that we have that an IV estimator may be inconsistent. For example, if the exclusion restriction doesn't quite hold. So it may hold to some extent, but there may still be a small correlation between the instrument and the error term in the second stage. If that's the case, and we have weak instruments, we will see that can lead to a massive inconsistency of the estimator. And if an estimator is inconsistent, then even in a sample that is of infinite size, it will not hit the right parameter. And as such, it's questionable if we can actually use this approach then to learn anything meaningful about the effect that we want to learn about. And the third thing that is somewhat related is that if we don't have a sample of infinite size, which is what we typically have, we have a small sample bias, with IV estimators generally. And if we have weak instruments, that small sample bias is even getting bigger. Okay, so there are lots of reasons why instruments should be strong. Now to look at this, let's first recall the general notation of the IV estimator, because we will need this then to understand the mechanics behind weak instruments. Okay, so if you remember the OLS estimator in matrix notation, where you have more than one or more regressors, is this famous x prime x to the power of -1 times x prime y. And so that's the famous OLS formula in matrix notation that every undergrad student learns to hate. Now, if we want to extend this to a two-stage least squares estimator, we have to basically incorporate the first stage in it, and this is done through this projection that we're doing in the first stage, right? So the first stage is a regression of the regressor of interest x onto the instruments. Or if we have more than one endogenous regressor, then we obviously have, we regress each of them on all of the instruments. So this is done, and it's the notation here in a compact way. How this is done is we have this projection matrix, which is basically the right-hand side of the first stage equation, and we use that to generate those fitted values of x. Okay, so remember, we have our endogenous regressor x, or here in this case in that matrix x, there are a couple of regressors, one or more, that are endogenous, and then we have instruments that are included here, and we use this projection matrix to purge from our endogenous regressors the variation that is purely due to the instruments and is therefore exogenous. And that's what we're doing here. And so that's why for the two-stage least squares estimator that you can see here, we basically have those two projection matrices incorporated here. And so the estimator looks slightly different because, again, we're only using the variation in x that is explained by the instrument. So that's why the two estimators, OLS and 2SLS, are different. And then comes the question of what does this do to statistical inference? Okay, so we know from master's or undergrad level econometrics that asymptotically the variance of the OLS estimator, it should actually have a hat here, that variance is as follows. It's the variance of the estimated variance, it's the variance of the residuals in our sample divided by this term here, which we will see in a case with just one regressor is just n times the variance of that regressor. So it has something to do with the variation of that regressor. Again, when we extend this to the two-stage least squares case, we will see that the asymptotic variance of our estimator is slightly different, because instead of using x, the matrix of regressors, we now use x hat here, which is the matrix of the predictions from the first stage. Again, we run the first stage, and then basically we only use the variation then so we purge the endogenous variation and then only use the exogenous variation in x, so the variation that is explained by the instruments. And so therefore this expression here in parentheses also includes this projection matrix, so it includes the first stage. And what is a bit hard to see here, but what you have to believe me, and I show you with a more specific example in the coming slides, is that if the first stage is weaker, this expression here becomes smaller, okay? And because we have the -1 here, which means basically we divide by that, that means also that a weaker first stage leads to a greater variance in the estimator and therefore greater standard errors. So what you can do is, if you just use a model where you have one endogenous regressor, that's K. So the regressor is called X, but K is the number of endogenous regressors and Q is the number of instruments. So you have to just identify a case. You have one instrument for one endogenous regressor. So the typical scenario that we encounter. What we can show there is that the formula that I've shown on the previous slide simplifies to this formula here. Now that's, and here we can see that that this offers some important insights. So let's first go through the components here. Again, the sigma hat squared is nothing more than the variance of the residuals. Okay, so this is sometimes also called the regression error. So anything that's not explained by my x variables is called the residual, and it's the variance in the residuals, or the variance of the residuals. So then we have n, which is just the sample size. We have sigma square x, which is just the variance in x. That would be the same in an OLS. So for OLS, the asymptotic variance of the OLS estimator would be simply sigma hat squared divided by n times the variance of x. Okay, so the additional term here is that correlation between the variance, the correlation between x and z as in the first stage. And that correlation is not exactly the first stage, but it's related to the first stage. So if we have an OLS regression, you can think about it as if we had a regression where the instrument for x is x, and then obviously the correlation there is 1, and then it cancels out. Whereas if we have an instrument that is correlated with the endogenous regressor x, but imperfectly so, that Pearson correlation is not 1, but is smaller than 1. Okay? And so what can we learn from that? So first of all, when you look at both these asymptotic variances up here, it shows that the larger the sample size, the lower is the variance. Okay, that remains the same. Also, the greater the regression error, the larger is the variance, and the smaller the variation in x, the larger is the variance. Okay, so in other words, if I want to have low standard errors, I need a large sample with lots of variation in my x variable and a model, a regression model that explains a lot of the variation in the outcome. Right? These three things are common to IV estimators and also general OLS estimator. But here's where the difference comes in because of this correlation here, because of the first stage. So what you can immediately see here is that the stronger the first stage, the lower is the standard error, and vice versa. So if I have a very weak first stage, I will necessarily have large standard errors. That's something that you cannot change. That's just how it is. Plus, you cannot compensate, for example, for having a small sample, you cannot compensate for the fact that you, because of the small sample, you have a large variance, that you then have a strong first stage. Why? Because the asymptotic variance is always, of the 2SLS estimator, of the IV estimator, is always bigger than the asymptotic variance of the OLS estimator. Right? Because there is this imperfect correlation between the instrument and the regressor of interest. And that's an important insight. So the inference, the statistical inference, will always be on more shaky grounds when you use an instrumental variable estimator than when you use OLS. Right? So you obviously do away with an endogeneity problem here if your instrument is valid, but you still have to you have a larger variance than with OLS. And obviously, if your first stage is very weak, then your variance can become very, very big. And that is obviously a problem, because if your variance is so big that the true value could be anywhere, that your estimate covers a range that your estimate is consistent with many true values, then there is not so much we can actually learn. So that was the first issue, which is that weak instruments inflate the variance. Now there is another problem, which is that weak instruments exacerbate the problem of inconsistency, which arises if the instrument is invalid. So you may have a scenario where the validity of the instrument, which is governed by that covariance, where that doesn't hold. And there are obvious cases where it doesn't hold, but there are many cases where you say, well, it most likely holds, but there could be this small probability that it doesn't. The problem is, if you have weak instruments, then in that case, even that small correlation between the instrument and the error term can lead to a huge inconsistency of the estimator. Okay, so then the estimate that we're getting is very far from the true value, even if the sample size goes to infinity. Now, to see this, what we're going to do is we're just going to look at a simple model where we just have one instrument and one endogenous regressor. And we're going to again compare OLS and two-stage least squares. Okay? So OLS is, again, it's just a projection of the outcome on the regressor here, whereas two-stage least squares is a projection of the outcome on the regressor that is predicted by the instrument. So then when we look at the probability limit of those estimators, so the value that the estimator takes when the sample size goes to infinity, what do we get here? Well, for the OLS, we get the true value, the true parameter, plus the bias term. Yeah, the bias term is there because initially we had the case that there was a correlation between the regressor of interest and the error term, and due to unobserved heterogeneity, measurement error or such. And once those problems are present, which they typically are, think about the examples of people selecting themselves into who attends a gym or not, or firms selecting themselves into exporting or not. You typically have this correlation present when you have non-experimental data, and so that's why we use an IV. When we do two-stage least squares, it looks very similar. We also have the true parameter beta plus a bias term, and if our instrument is valid, then obviously that bias term disappears, because if the correlation between the instrument and the error term is 0, then the correlation between whatever is predicted based on the instrument and the error term is also 0, because it's just a linear transformation. However, suppose that correlation here, this one, is not 0. It's small. Then we have potentially a problem. And the problem is exacerbated, as I will show you, by weak instruments. So how can we see this? What we do now is we have here the relative inconsistency. Okay, which is basically just the two bias terms in one bias term divided by the other, right? And even though I call it bias, this is not about bias in terms of the expectation of the estimator being different from the true value. Here we're talking about the relative inconsistency, which is that as the sample size goes to infinity, we are not hitting the true value. Okay, so we have so what I did here was I just rearranged these these bias terms. And what's very handy is that now we have in the denominator the variation in the predicted x divided by the variation in the x variable, and that can be shown is nothing more than the r squared of the first stage. So how much the first stage explains. So how much the instrument explains of the regressor. If that is low, there is no correlation. If that is 1, then the instrument perfectly explains the regressor. Okay? So again, this r squared is just a measure of the strength of the instrument. And now you can immediately see what's going to happen. If the instrument is 1000% valid, so if this covariance between the error term in the second stage and the predicted regressor, if that is 0, I don't need to worry about the strength of the instrument unless it's 0. But if it's because then that's obviously not defined, that fraction. But if it's non-zero, if it's even just small and positive, I don't have a bias and my estimates are consistent. However, if that covariance up here is different from 0, is slightly bigger, then the extent to which an IV estimator is inconsistent relative to an OLS estimator depends very much on the strength of the instrument. If the instrument is strong, it's not such a big problem. If the instrument is if the instrument is very weak, then that can be a huge problem. Okay? Because what you're doing here is basically you're dividing something small by something small, and that can become very big, right? So if let's say the bias here at the top is 0.1 and the first stage of r squared is 0.01, then you have all of a sudden a factor 10, that the relative inconsistency OLS would be 10 times more inconsistent than, IV would be 10 times more inconsistent than OLS. But obviously, if you have now instead an r squared here of 0.9, that the two of them are very highly correlated, then for the same violation of the exclusion restriction, you have a much smaller problem. Yeah, so the weaker my instrument is, the more does it exacerbate any violation of the validity of the instrument. That was problem number 2. Problem number 3 is a general problem of instrumental variables, which is IV estimators they give you, under the best of conditions, a consistent estimate, but not an unbiased one. And the reason is that we have inevitably a small sample bias. And so think about this very carefully. This has huge implications. If you have a sample of infinite size, or a very large sample, then and your IV is valid, then it would converge to the true parameter, to the true effect that you're interested in. But if you have a small sample, then even though theoretically, if you let the sample size go to infinity, it would hit the true value, the value that you're getting, even in expectation, may actually be quite far away from the true value. And so that is it, and that problem is also exacerbated by weak instruments. Okay? And why the intuition, to develop the intuition for that is not so straightforward. So let me give it a try. Now what we're starting with here is an instrument that is completely uncorrelated with the endogenous regressor. Okay? So what that means is that in the population with infinite data, so infinite number of data points, we don't have any covariance between the instrument and the endogenous regressor. And so obviously there you can't even compute the IV estimator, because the IV estimator in its simplest form is the reduced form divided by the first stage. And obviously if that's 0, the first stage, then you can't even compute the IV estimator. It just goes to infinity, and you can't say anything meaningful about it. But if you instead have a small sample, then in your sample, it may well be that this covariance between X and Z, the first stage, may actually be different from 0. And not because it's 0 in the real world, but simply because you just, through a coincidence, got a sample where it's not 0. And so the first stage is then completely driven by noise, completely driven by sampling variation, and has no meaning whatsoever. It does not contain any information about the regressor whatsoever. And that's a general insight of instrumental variable estimators. In any finite sample, there will always be some random correlation between the error term and the instrument. Yeah? And simply so it will always pick up, your instrument will always have some small correlation with the noise in your model. And so this means that even if your instrument is valid in theory in a sample that goes to infinity, in your small sample, the exclusion restriction may still be invalid, okay, or may still be violated. And so if you are in this world where you have no first stage in the population, but in your sample you do have a first stage because of sampling variation, that sampling variation does not purge the endogenous variation from the regressor of interest. And so therefore you will inevitably have a small sample bias, and again the bias will be bigger the bigger is, or the weaker is, your first stage. So to see this, we can go back to this formula here, and just think about it here in terms of expectations rather than probability limits. So in terms of expectations means that you take an infinite number of small samples from an overall population that you're interested in, then with weak instruments, that expectation may, first of all, not even exist. But if you then just look at one particular estimate, you may well get a you may get a positive variation in the predicted regressor of interest. And again, that exacerbates then any violation of the exclusion restriction. So first of all, it exacerbates that, and second, it may actually introduce that correlation in the numerator of that bias term. Okay, so because of the small sample, you always have that little correlation. So let me draw this in green that you see what I'm talking about here. So because we're in a small sample, we have this correlation here inevitably. It may be small, but it's there. And then because we have a weak instrument, because this what's here in the denominator is very small, that sampling variation that gives you that correlation between the instrument and the error term, the bias that comes from that actually gets exacerbated. And that again is also a huge problem. So put this all together, there are three reasons. Admittedly, the inconsistency and the small sample bias, they sound as if they were the same. They are related, so the mechanics are very similar, but they're not the same source of bias. Small sample bias is bias that's basically inbuilt due to the fact that we have a small sample and we have sampling variation in the first stage because of that. The inconsistency comes from outside, basically from the instrument not being fully valid. Yeah, but mechanically, they then give you very similar, or cause you similar trouble. So the question is, what can you do about it? There have been a few tests that have been developed over the years that allow you to see, well, is my first stage strong enough to draw any meaningful conclusions about the parameter I'm interested in? And this is a literature that is currently evolving, so you have to stay up to date. So until the mid-2000s, there has been the literature has pretty much converged towards a rule of thumb. And that rule of thumb was that if the F statistic of a test of significance of your instruments in the first stage, if that was greater than 10, that means that the instruments are sufficiently strong. That's what a paper by Stock et al. Has shown, and also previous papers by that group of authors. But note here that this is a rule of thumb. They've just shown in, numerically and through simulations, they've shown that if the F statistic is greater than 10, that in most cases you can draw a reliable inference. But I will show you that it's not that easy. That may be a first pass for your instrument, but it's by no means sufficient to draw any meaningful conclusions. So here's an interesting paper that came out a while ago by Alvin Young, called Consistency Without Inference. And what he does is he takes from the journals of the American Economic Associations, he took 1,300 IV estimates. So, if a paper reports 20 estimates, he takes all those 20 estimates. So there are not 1,300 IV papers in those journals, but there was lots of estimates reported. And what he does is, so on the websites of the AR and the AEJs, you can get the actual data that the authors used. And what he does there is the following, that he takes those data sets, and instead of computing the standard errors through the conventional parametric procedures that these authors use, he uses non-parametric procedures. So bootstrap and jackknife. And what he shows there is that in most cases, the results are actually driven by very few observations. So if you have those observations in your sample, the first stage is there. And if you don't have those observations in that sample, the first stage is not there. Does that mean the authors did anything wrong, or was this malpractice? No, it's just that the parametric assumptions we make about the error terms, which then allow us to calculate the standard errors, they don't capture that. That's what he has shown. And consequently, the F statistic that we then use in this test are these coefficients in the first stage significantly strong, is also doesn't reflect that. And that was a huge discovery. And obviously econometricians had talked about this before, but he has shown that this is a really big problem. And in the bootstrap, you can see that, because in a bootstrap sample, you draw observations with replacement, and especially when you have a sample that is very small and where you have the first stage reliant on just a couple of observations, you have many bootstrap samples in which these observations with very high leverage are simply not included. And so that's he showed basically the distribution of estimates and showed a much wider sampling distribution of the IV estimators than what the parametric distributions would have been that the authors assumed. So that was a wake-up call for many people to say, okay, it's actually not as harmless as it seems. Even though we can test for weak instruments, it may not be as harmless. Now, there was another wake-up call, and even much stronger, by Lee et al. In a paper that came out recently, who basically looked at the practice of most applied econometricians of using that F statistic of F greater than 10. And once that's the case, they simply draw inference on that parameter beta using the conventional critical values for whatever significance level they want. So 1.96 for a significance level of 5%. But what they show is that, again, because you have your instrument only uses a fraction of the variation in the regressor, that actually you would need a much higher F to get reliable inference at the 5% level using those critical values. And so they showed that in their simulations, the F that you would need would be 143. And when that came out, everyone looked at their IV papers where you have F statistics typically 30, 40, if you're lucky, 60, 70, 80. But that's an extraordinarily high F. The good thing about it is they provide critical values, and the idea is not to say any study with an F lower than that is meaningless. By no means. I mean, in general, in statistics, whenever there are those rules, reject or do not reject based on an arbitrary threshold, we should be very careful. And here, the solution is actually that we have to use larger critical values. So for a given sample size and so on, we have to use critical values that are greater than 1.96 if we want to draw inference at the 5% level. And obviously that makes it less likely to detect a statistically significant effect at any level, but fine, that overcomes also a huge weak instrument problem. Another thing that you need to be aware of is that a lot of the traditional tests for weak IVs, also the Kleibergen-Papp tests that, apologies, not the Kleibergen-Papp, but the conventional F statistic that your statistical software spits out when you run an IV regression, that does not account for things such as heteroscedasticity or autocorrelation, be it serial or spatial, or clustering. So it does not account, in other words, for any dependence in the error terms, either dependence on X or the correlation between error terms. And so if you use the conventional F statistic and then draw inference, then the standard errors of your estimator are also too small. And you may also see that your instruments appear stronger than they actually are. That's the problem with that. So the alternatives are the following. So Kleibergen and Papp developed F tests that are robust, although it has recently been shown that as one econometrician put it, they get the standard errors right, but they don't exactly estimate or allow you to estimate the right thing, namely an actual test statistic for whether your instrument is strong or not. To what extent that is true, you have to read it yourself. But there is another method by Montiel-Olea and Pfluger that basically takes the conventional F statistic and scales it up in a way that it gets the standard errors right on average and allows you to get a meaningful test of whether your instruments are weak or not. And so this is definitely something that you should take into account, and basically anyone writing an IV paper these days should actually report those standard errors. So these are the recommendations when you write an IV paper regarding the instrument strength. Okay? We've seen that weak instruments cause all sorts of problems because they inflate the variance. They really complicate statistical inference and then also exacerbate things like the inconsistency if the exclusion restriction doesn't hold, and they exacerbate the small sample bias that is inherent in IV estimation. So what we can do is, well, first of all, we should use, for statistical inference to begin with, we should use the critical values from that paper by Lee et al. We should not just use the inbuilt statistical tests with 1.96 for a 5% confidence level. We should use more conservative values. It's also advisable to report the effective F statistic that takes into account things like clustering and so on, and has a more reliable, if conservative, procedure for determining whether your IVs are weak or not. Then, if you find that your IVs are weak, don't discard the paper. Also, don't discard or don't, if you're a referee, don't recommend the rejection of a paper just because the IVs are weak. Because there are methods that are based on a seminal paper by Anderson and Rubin many years ago that actually allow you to draw inference based on methods that are robust to weak instruments. And there are this literature has somehow been dormant for many years, but has been picked up in the last 15 years or so. I'm giving you here two references of papers that have shown how robust inference can be drawn, and also provide statistical procedures to do that in inbuilt Stata and R routines. Now, if you want to learn more about weak instruments and the recent developments, I recommend this review article by Andrew Stock and Son, which has a lot more on that topic. But it's definitely something that if you plan in the next years to write an IV paper, it's definitely a literature that you have to be aware of, and then you have to probably apply methods that are only about to come out in the next couple of months, if not years.